So in this problem, you're given 5 different functions. In the first 2 parts, a function defined by a data table. In the parts C and D, a function defined by a formula. And then in part E, which we'll talk about first, functions defined in terms of graphs. So looking at these 2 graphs, I claim that one of them is the graph of an invertible function. One of them depicts the y-coordinate as a function, an invertible function of the x-coordinate. One does not. So which one does give me the invertible function, the R graph or the S graph? The R graph. How do we know that the R graph is the one that gives me an invertible function? What are we looking for? Yeah, which line test? Horizontal line test. Great. Any horizontal line that I can draw on this graph, no matter where I draw it, right, is only going to intersect the graph how many times? Once, no matter whether I draw it there, or anywhere else, right? And anywhere that I choose to draw it, the one place at which it intersects the graph is going to give me an ordered pair. Oops. This is the ordered pair -1, 2. So how would I write this as R inverse of something equals something? R inverse of what is equal to what? R inverse of 2 is equal to -1. Great. Okay, we can fairly quickly dispatch with this graphs part. So that one's invertible, and how can I tell that this one's not? What's an example of a horizontal line that meets this graph more than once? At -3, well, -3 is down there. Positive 2, well, positive 2, nudge it down a little bit. Yeah, in between 1 and 2, like, I don't know, y equals 1.5 or something like that. Right, that line, that horizontal line is definitely meeting this graph twice. And so, not invertible, does not pass the horizontal line test. Okay, let's jump back to the data tables. I'm suggesting here that one of the ways we can understand what a function is doing is using one of these hunters and arrows diagrams. So here the domain and the range of these functions are both just these finite sets, and so it's easy for me to just kind of draw them as just by listing out all their elements. So my first f function here is taking the elements 0 through 4, and it's sending them to these targets, 0, 1, 2, 3, and 4, sort of listed like this. Same thing with g. So again, I claim one of these is invertible and the other one is not. Which one is invertible, f or g?
G.
G. How do I know that g is invertible? All inputs have an output. A single output, yes, invertible. So what's the problem with the f function? For which value can I not find f inverse of blank?
0.
F inverse of 0 doesn't exist, for starters. What's another? Yeah, f inverse of 2. Why is f inverse of 2 bad?
2 outputs.
Right, it would have 2 outputs. Right, so 0, even if there were an inverse function, 0 would not be in the domain of the inverse function. And moreover, there cannot be an inverse function because the input 2 to the inverse would have 2 different outputs, namely 4 and 1. Okay, so formulas. Part C, we started with the formula P equals 7 minus 3/5 t, and then we put an exponent of 4 on it the second time around. Again, I claim one of these was invertible and the other one was not. Which one is definitely invertible? The one without the exponent, because if I just rearrange this equation to solve it for t, I get a formula right here. T equals -5/3 times p minus 7. And I could call this, let me just call it f inverse of p. I get a formula for the inverse function, because any p-value that I choose, any single input to this inverse, is going to give me a single value for my output. So why doesn't that happen when I have an exponent of 4 in here gumming up the works? What's the last step in solving this equation for t? What do I have to do to both sides? I should take not the square root, but the 4th root of both sides. So I'll do that. It's the root with an index of 4 in there. Index of 4. Okay. And so on the left-hand side, I'm going to get this nasty thing, the 4th root of -5/3 times the quantity p minus 7. But what do I get on the right-hand side of this equation? What happens when I take the 4th root of t to the power 4? It cancels out, but something is left behind. Yes, something is left behind. Namely, what's left behind is an absolute value. So that's the subtle piece of this, right? And why is that? What is it about this root and this radical that tells me that that's going to happen? It happens for square roots. It's an even index. And for any even index root, this absolute value shows up here, because any even power of a negative number is the same as that power of its corresponding positive value, right? Negative 5 to the fourth power is the same as positive 5 to the fourth power, right? And so even powers erase signs. It no longer lets us tell the difference between positives and negatives. And so when I go backwards and undo an even power, we always create multiple possibilities. So when this absolute value goes away, it becomes a plus or minus on the other side. Plus or minus the fourth root of negative 5/3 times p minus 7 equals t. Now, how do I know that this is not a formula for a function? If I have a single p value, how many t values do I get generally? I generally get 2, right? One of them with a plus sign and one of them with a minus sign, right? So that's not going to give me a function. And just to tie a bow on it today, if we were to graph this function, 7 minus 3/5 t to the fourth. So the graph of the function, p of t, equals 7 minus 3/5 t to the fourth. Yeah, there's my graph. And sure enough, this graph does a pretty poor job of passing the horizontal line test. But remember, is there a way for us to make this graph pass the horizontal line test? What do I have to do to it? Yeah, I can just cut it down. Just erase some of its domain. Let's say I just take t greater than or equal to 0. So I'm just going to take a piece of that graph. What about this? Passes the horizontal line test?
Yes.
Passes the vertical line test? That looks good. And sure enough, if I take and graph y equals the fourth root, so something to the power 1/4. What did we say the formula for that was? 5/3 times the quantity p minus 7 or something like that, right? It turns out that, oh, hey, look, there's a graph of that part of the inverse. Right? By the way, what's the relationship between these two graphs? Does anybody see it?
Inverses?
They're inverses how? Yeah, notice some hand motion going on there. Yes, right. One of them is actually a reflection of the other. Actually, I think I might want the minus here. No, sorry. This is, I think, 7 minus x, not x minus 7. Yeah, there we go. Oh, that makes a lot more sense. Right. In fact, take a look at how the two of these are related. The blue curve, the graph of the inverse, is exactly the same shape as the red curve, the graph of the original function. It's just been reflected across this diagonal line. And this diagonal line is the line y equals x, right? What happens when you reflect across y equals x? You interchange the x coordinate with the y coordinate, which makes sense because that's what we're doing in an inverse, is we're trading places between the role of the input and the role of the output.